So today it will be our goal to finish section 4 of chapter 10. We've been talking about polar coordinates. We've been talking about how to graph polar equations where r is given as a function of theta, okay? And what some of those polar graphs look like, how to do it. Yesterday I showed you a technique, well, multiple techniques, one of which is to just convert the polar equation into a rectangular one and see if we recognize it, okay? That won't always be possible to do. Sometimes you'll convert and realize, oh man, this is just a circle. Okay, and we did that in one of the cases, like when r was equal to 6 sine of theta, for instance. But that won't always be possible to do. There will be times when you convert from a polar equation into a rectangular one, and you'll be like, I have no clue what that is. That's just a disaster of x's and y's. I have no clue what kind of a graph that is. And so you have to resort to doing things like making tables. But I think the best way to make a table is to actually graph the thing in the r theta plane and then translate that over to the xy plane, yes? So hopefully that kind of made sense yesterday when we were doing that. Are there any questions, any lingering questions on that? Any questions at all? Well, okay, so today, what I'm going to do is show you how to take the derivative of a polar graph. Because we know how to take derivatives of a parametrized curve, yes? Remember dy dx was like dy dt over dx dt. So we could find what the derivative was at various values of t. Turns out that we're going to be able to do that for polar equations as well, just by using what we knew about general parametrized curves. Okay, so let's look at that. So derivatives and polar coordinates. So dr d theta would give the rate of change of r with respect to theta. Yeah. So if I have r being some kind of function of theta, then dr d theta would give the rate of change of r with respect to theta. But that's not necessarily what we're interested in. We want to find dy dx where y is given by r sine of theta and x is equal to r cosine of theta, yes? So we don't necessarily care about how r is changing with respect to theta. That would be more like what we had in that r theta plane over there. We want to think about what's happening over in the xy plane when we convert to polar coordinates. Okay, so that's going to be our primary goal. So we want to find dy dx given that r is equal to some function of theta. So maybe, maybe, let me just kind of write this in here. Maybe I have something like, so maybe like r is equal to 6 sine of theta, for instance, yes? Okay. And if I took dr d theta, that would basically just give me what the derivative was in the realm of r theta, not in the realm of xy. Okay, I know I'm just repeating myself, but I want to make sure you know that you can't just take dr d theta and say, well, that's the derivative. What you really want to know is what dy dx is if x and y are converted to polar coordinates. Okay? So x is equal to r cosine of theta, but of course, r itself is given by f of theta, which is why, we replace r with f of theta. And same thing here. You replace r, you replace r with f of theta, okay? X is r cosine of theta, y is r sine of theta. And now we're going to use what we know about derivatives of a parametric curve. dy dx, this was the formula we came up with, right? You have to take dy d theta, and you have to divide that by dx d theta, okay? Which means I'm going to have to, because theta is like the parameter in this case, correct? Theta is the parameter that controls everything, including the radius. The radius changes with theta, okay? So we need to figure out what dy d theta is and what dx d theta is, okay? Well, to compute dy d theta, right, here's y right here. Y is like some function of theta times sine of theta. times, which means we have to use the product rule, correct? So do you guys see where this is coming from? dy d theta is going to be f prime of theta times sine of theta, right? That's the derivative of the first times the second, plus the first, which is f of theta, times the derivative of the second. Well, what's the derivative of sine theta? Cosine theta, yeah? So that's what dy d theta ends up being. Whatever f of theta is, whatever r is given by in terms of theta, you simply multiply the derivative of that by sine theta, and you add r again times cosine of theta. Okay. And what about dx d theta? Well, similarly, here is what x is, and if I want to take the derivative of that, it's going to involve using the product rule again. It's going to be f prime of theta times cos theta plus the first, which is f of theta, times the derivative of cos theta. But what's the derivative of cos theta? Negative sine. Okay, so you get negative f of theta sine theta. Okay? So now we have a formula for the overall derivative. dy dx equals f prime of theta sine theta plus f of theta cos theta, right? That's what dy d theta is, over f prime of theta cos theta minus f of theta sine theta. That's sort of a complicated looking formula, but how we came up with it wasn't really all that bad, okay? So that's the formula for dy dx if we have converted to polar coordinates, okay? So once again, remember that r is equal to some function of theta here. That's what f of theta is, okay? R, the radius, is given by f of theta. So really, I mean, if you think about it for a second, this guy right here is r, and this guy right here is r. And what's this guy? That's really just dr d theta. So dr d theta does play a role here, and this guy right here really is just dr d theta, okay? Okay, are we good so far? Because we're going to use this to actually compute some derivatives of these polar curves. Are there any questions so far? Anything? Okay, so that's our little formula there. Okay, I've repeated it right here on this slide. So you see dy dx is given by that equation. Once again, just to remind us, this top part right here, that's what we discovered dy d theta is. And this guy down here, that's what we discovered dx d theta is. Okay, where once again, x is equal to r cosine of theta, and y is equal to r sine of theta, and r, of course, is just some function of the angle theta. Okay? Well, when will we have a vertical tangent line? Well, whenever the denominator is 0. Yes? If the denominator is 0, we will have a vertical tangent line. Most of the time, unless the top is also 0 at that angle, yes? If the top and bottom are 0 at the same time, then there's some conflict. When will we have a horizontal tangent line? Well, that will happen when the numerator is 0, correct? Because then dy dx would be 0, yes? So if the numerator is 0, then we will have a horizontal tangent line. That just means dy d theta is 0. And we can't really draw a conclusion if both the numerator and denominator are 0. That's a problem. Okay, we have to kind of think about that separately. So does this statement make sense? You have a vertical tangent line basically when the denominator is 0. You have a horizontal tangent line basically when the numerator is 0. Unless both of those things happen at the same time, in which case you're going to have to think more carefully. Make sense? Hopefully. All right. So we're going to do some examples here. Okay, so here's the equation. Here's kind of the direction that we're moving in. Now let's look at some examples here. So r equal to 1 plus sine of theta, which is almost like that exciting graph we looked at last time. What was the graph? What was the heart graph? Do you remember? 1 minus sine of theta, yes? That's right, that was exciting, right? So 1 plus sine of theta, 1 plus sine of theta, that changes the game a little bit, okay? I'll show you what the graph of that looks like here pretty soon. So first I want to find dy dx. Remember, we're always assuming that x is, x is equal to r cosine of theta and y is equal to r sine of theta as we convert to polar coordinates, okay? And so dy dx is given by that formula on the previous page right there, yes? Just so we are on the same page here, okay? So what is dy dx? Well, y is r sine of theta, yes? But r, of course, is given by 1 plus sine of theta, yeah? So do you see what I've done there? I've just replaced r by what it is, yes? Okay? Okay? And then I get this. Okay, I just distributed sine of theta in here. And we ended up getting sine theta plus sine squared theta. Okay? And what is x? Well, x is, once again, that's r right there. X is given by r cosine of theta. Replace r with what it is. Distribute the cosine. And we have it here. We have what's written right here. And in this case, it's almost easier to just straight up compute dy d theta and dx d theta separately, yes? I have what y is in terms of theta. I have what x is in terms of theta. Let's not lose our collective minds and go back to that equation we had on the previous slide necessarily. Dy dx will just be dy d theta divided by dx d theta, okay? So what is dy d theta? Well, look at that. I have y sitting up there. Dy d theta is derivative of sine is cosine. What's the derivative of sine squared of theta? Well, I would have to use the chain rule. It's going to be 2 sine of theta to the first times the derivative of sine, which is cosine. All right, so there's dy d theta. And what about dx d theta? Well, I have to take the derivative of cosine, which is negative sine. And then what am I going to do with sine theta cos theta? I would have to use the product rule. Okay, so it would be the first, which is sine times the derivative of the second. What's the derivative of cosine? Negative sine. This is going to be sine times negative sine, which is negative sine squared. Yeah? Plus the derivative of the first times the second, but that's just the derivative of sine, which is cosine times cosine, which is where the cos squared comes from. You see what I'm saying here? This part right here simply came from the product rule, right? The product rule, okay? So I have dy d theta, I have dx d theta. So if I want dy dx, I just have to take the ratio of those two, yes? Okay, so dy dx is equal to, right up here, up top, that's dy d theta. And down below, that's just dx d theta. Okay, so that's where that comes from. And I've kind of highlighted a couple of things in blue right there. Do you see that? Oops, hang on, I'm gonna erase this. I've highlighted a couple of things in blue. What I'm going to do is replace, I'm going to make everything in terms of sine in the denominator, just so it's a little bit easier to work with. So what do you think I would replace to make everything in terms of sine, so I don't have to work with 2 trig functions at the same time? I'm going to write everything in terms of the sine function, okay, in the denominator. That means I need to get rid of the cosine stuff. How? How would I do that? What would I replace cos squared with? 1 minus sine squared, of course. I'm going to replace this with 1 minus sine squared of theta. And therefore, I would have 1 minus 2 sine squared thetas minus another sine theta. Yes? Okay, so I just wanted to make sure you knew where this next line is coming from. Okay, so basically that cos squared gets replaced by 1 minus sine squared. And so that denominator is now completely in terms of the sine function. And what did I do to the numerator, just to make sure we're on the same page? What did I do to the numerator? Hold out the cosine. And what's left behind is 1 plus 2 sine of theta. Now remember, the reason I'm doing this is because if I wanted to figure out where the tangent line goes vertical, I would need to easily be able to determine where the denominator is 0. To figure out where the tangent line goes horizontal, I would need to easily be able to figure out where the numerator is equal to 0, yes? So tangent line vertical, denominator 0. Tangent line horizontal, numerator has to equal 0, yes? So does that formula make sense? Hopefully. By the way, this guy factors. Do you realize that? How does that factor? Do you guys, it's like 1 minus, hang on a second. So I think it's 1 minus 2 sine of theta times 1 plus sine of theta. Is that right? Does that work out okay? If I were to multiply that out, think about it for a second. Wouldn't it be 1 minus 2 sine theta plus sine theta, which is just minus a single sine theta? And then it would be minus 2 sine squared theta, yes? So that denominator actually factors nicely, which is something that we'll use here pretty soon, yeah? That's one of the advantages of completely switching over to having things in terms of the sine function. Okay, any questions on that? Because we're about to kind of use this formula in this example. Any questions at all? Well, okay. Find the slope of the tangent line when theta equals pi over 3. Okay, so first of all, it would be nice to know what point I'm talking about if theta is equal to pi over 3. Do you know what I'm saying? Theta equal to pi over 3, what point are we at? Let's kind of ask that question first. What point are we at if theta is equal to pi over 3? Well, I would have to plug theta equal to pi over 3 in for theta. Yes? Guys, this is where if you're sort of ill-equipped to deal with trig functions and kind of remember some basic values for the trig functions, this is where we need to kind of shore up some of that understanding, okay? Because we need to quickly be able to compute things like sine of pi over 3. What is sine of pi over 3? Do you know? What's that? Radical 3 over 2. That's right. So r at this point it is 1 plus radical 3 over 2. Okay? So the point we are at is 1 plus radical 3 over 2. Like radical 3, I don't know. That's basically like, radical 3 is like 1.7 something, correct? If I divide that by 2, you know, I don't know, that's like 0.85 something or whatever, okay? So this is basically like 1.8-ish or something. That's what the radius is, okay? And the angle is pi over 3, okay? So this is the point r comma theta that we are sitting at on the curve. Does that make sense? So which quadrant are we in, by the way? Which quadrant does this live in? Quadrant 1. Okay, the radius is positive. The angle sits in quadrant 1. We're at 60 degrees, okay? Okay, so let me just say that the point we're at is r theta. I'm just repeating this. 1 plus square root of 3 over 2, pi over 3. And this is quadrant 1. Okay, quadrant 1. Okay. But I want to know the slope of the tangent to that point. Well, I would straight up use the formula that we just had on the previous slide right there. Right, I have dy dx. I would plug in the parameter value, theta equal to pi over 3, yes? I'm at that point, 1 plus radical 3 over 2 comma pi over 3 on the graph. And I would use this formula to figure out what the slope is. Okay, plug in pi over 3. What's the cosine of pi over 3? Do you remember? A half. And the sine of pi over 3 is radical 3 over 2. Okay, so I plug that in. 2 times radical 3 over 2 is just radical 3. Cosine of pi over 3 is 1/2. On the bottom, I have 1 minus radical 3 over 2 minus 2 times radical 3 over 2 squared. But radical 3 over 2 squared is like 3/4. Do you understand? What's 2 times 3/4? 3/2. Yes? Okay. That's interesting. And I am telling you, believe it or not, this is sort of amazing. Look, if I multiply this by 2 over 2, what happens here? Well, the top just becomes 1 plus radical 3. Do you know what I'm saying? Over, if I multiply the bottom by 2, I'm going to get 2 minus radical 3 minus 3. You see what I'm saying? Yeah? Because it's going to be 2 times 1 minus 2 times that. And what's 2 minus radical 3? What's 2 minus radical 3? -1. Okay, so that's going to be -1 minus radical 3. And hey, do you guys realize that the bottom is just the negative of the top? Yes? Okay, so this is -1. That's what I'm saying. Like we're just doing a little bit of arithmetic here. Okay, so that slope is -1. And that's interesting. Okay, -1. The slope of the tangent is -1 to this point. Oops, I stinking erased that thing. It's 1 plus square root of 3 over 2 pi over 3. That's our r comma theta that we're sitting at. Yes. The slope is -1. I know the point. I know the slope. I could write down the slope of the tangent line if I really wanted to. Yeah, or the actual equation of the tangent line actually. Okay. I have the slope. I know what point I'm at. I could write an equation of the tangent line if I were so inclined. What does the graph of this thing look like? Well, you expect it's going to be some kind of heart-shaped thing, yes? We all remember what r equal to 1 minus sine theta looks like. How much difference could we have if we just swap the plus for, or the minus for a plus? Okay. Indeed, the thing looks like this. Okay. It's a flipped upside down cardioid, yeah? Is that really that surprising that the whole thing just went like that? Okay. And again, this is that point right there. And the slope here, what's the slope of this? That we just discovered the slope is -1. That's right. So this angle right here is pi over 3. And this distance right here out to this point, the distance out to that point is 1 plus radical 3 over 2. Okay. Make sense? Yeah, we had the formula for the derivative. We're able to kind of figure out what the slope of this tangent is, and we know everything about it. That's good. Okay. All right. Next part. So if r is equal to 1 plus sine of theta, find where the curve has horizontal and vertical tangent lines. Now, where are we going to have horizontal tangent lines? When will the tangent lines be horizontal? Generally speaking, not necessarily for this example, but generally speaking, where will the tangent lines be horizontal? When the derivative is 0, yes. Which that will happen when which is 0, the numerator or the denominator? Numerator, yes. And the numerator is dy d theta. Remember, so dy dx is equal to dy d theta over dx d theta. Okay, so the tangent line will be horizontal if dy d theta is 0. Yes. The tangent line will be vertical if dx d theta is 0, unless both happen simultaneously, in which case I have to think carefully about what's going on. Yeah. Okay. All right. Horizontal, well, that's when dy d theta is 0. Okay. But dy d theta is given by that. That was what the numerator was, right? Let me just go back over here, right? The numerator, dy d theta, is cos theta times the quantity 1 plus 2 sine theta. Yes? I just want to make sure we're on the same page here. So we set dy d theta to 0, which, what does that mean? If that's 0, what has to be going on? One of two things. Either cosine of theta is 0, or 1 plus 2 sine of theta is 0. Yes? One of two, those two things are the only possibilities. Hey, where is cosine equal to 0 when I'm between 0 and 2 pi with my parameter here? Yes? By the way, that cardioid shape is going to be sketched out precisely for the angles from 0 all the way to 2 pi. It'll sketch that out one time, okay? But where is cosine of theta equal to 0? Pi over 2 and 3 pi over 2. 90 degrees, 270 degrees. Where is 1 plus 2 sine theta equal to 0? Well, that would mean that sine theta is how much? Negative 1/2. Negative 1/2. Huh, all right. Where does that happen? 7, right? So it's like 30 degrees below the negative x-axis, okay? Which that's 7 pi over 6 basically, or 30 degrees below the positive x-axis, which is 11 pi over 6, yes? Because I want to stay in the range between 0 and 2 pi, okay? So the first one is fairly easy. That's either 90 degrees or 270 degrees. The other one, that happens at 7 pi over 6 or 11 pi over 6, as Jared surmised. Yeah? Does that make sense? 30 degrees beyond the negative x-axis or 30 degrees below the positive x-axis. That's where those two angles come from. So all four of these are potentially places where the tangent line is horizontal. Potentially. Okay? Why did I say potentially? Because what could happen? That's right. You could also have a 0 in the denominator. Does that make sense? Okay, so all four of these are potentially places where the tangent line is horizontal. By the way, let's go take a let's go take a peek at the graph for a minute again. Yes? Now, let's commit this to memory. Pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6. Places where the tangent line potentially goes horizontal, yes? Let's see if we suspect that if that's true. What about pi over 2? Does it look like pi over 2 is where that happens? Right, pi over 2 is right here, yes? Does it look like we have a horizontal tangent line there? Yeah, definitely does. What about 11 pi or 7 pi over 6? That's like, I don't know, right here. Yeah? See what I'm saying? Yep, that's 7 pi over 6. Of course, this going up to here, that was pi over 2. Okay, does it look like there's a horizontal tangent line there? Definitely. Okay, and what about 11 pi over 6? Whoop. Okay, that's 11 pi over 6. Yes? Does it look like there's a horizontal tangent line there? Most definitely. What about 3 pi over 6? What does it look like is going on there? Or sorry, 3 pi over 2. 3 pi over 2, 270 degrees, that's like down here. Does it look like I have a horizontal tangent line there? No, it looks like something else is going on, right? So we have strong suspicions that something strange is happening at 270 degrees. But the other three seem like we're good to go, right? Okay. Any questions on that? Okay. So we have these guys right here. Okay, pi over 2, 3 pi over 2. And it seems like this guy right here is a suspicious one. Yeah. But the other ones seem like they're really producing something that makes sense. Okay. All right, vertical tangent lines. There, we're going to have dx d theta being 0. Now remember dx d theta? That was the one where we replaced everything and made it in terms of sine. Yes, do you remember that? It was like 1 minus 2, or it was 1 minus sine theta minus 2 sine squared of theta. And I factored it, which is something that will be needful here in just a second. So I had 1 minus sine of theta minus 2 sine squared of theta equaling 0. We factor it like that. So one of two things is going on. Either 1 plus sine of theta is 0, or 1 minus 2 sine theta is 0. Yeah? Okay. Which is what I wrote right there. Okay, so that means that sine of theta is either -1 or the sine of theta is 1/2, correct? Okay. Where is sine of theta equal to -1? 3 pi over 2. Ooh, what is that? What does that remind you of? Didn't we have 3 pi over 2 distinguish itself on the last part where we had horizontal tangent lines? Okay, 3 pi over 2. What about sine of theta equal to 1/2? When does that happen? Quadrant 1 and quadrant 2. 5, right, pi over 6 and 5 pi over 6. That makes sense? Either 30 degrees off the positive x-axis or 30 degrees off the negative x-axis. Yeah? Okay. So there it is, 3 pi over 2 or pi over 6, 5 pi over 6. Now, one of those we know was a suspicious guy. Does that make sense? Because that was also a 0 for the numerator. But these two, we're pretty sure we're good to go on. Let's kind of go back and take a peek at pi over 6 and 5 pi over 6 and see if something interesting is going on. Okay? So where was the graph here? It was back over here. Okay? Where's 5? Okay, pi over 6. I don't know. It's probably like right here or something. 5 pi over 6. Okay, so this is pi over 6. This is 5 pi over 6. 5 pi over 6, so that would be like here and here. Does it look like we have vertical tangent lines there? Sure. Yeah, so vertical tangent line there and there. But what about 3 pi over 2? Okay, 3 pi over 2 is down here, right? If you go all the way down to right there. Does it look like we have a vertical tangent line there? Well, maybe. It looks like we might have like a little cusp right here, right? And maybe there is like a vertical tangent line of some kind. Yeah? We'll have to think about that in a minute. So actually, what was distinguished as potentially being a horizontal tangent line actually might end up being a vertical tangent line because it's a 0 of both the numerator and the denominator, okay, which is interesting. Okay, so here we go. There are horizontal tangent lines when theta is equal to pi over 2, 7 pi over 6, and 11 pi over 6. And vertical tangent lines when theta is pi over 6 and 5 pi over 6. But 3 pi over 2 is kind of a mystery, okay? Although when you look at the graph, it actually looks like the tangent line might be what? Vertical, because it kind of pinches in like this. Does that make sense? Looks like it might actually be a vertical tangent line, okay? But let's give 3 pi over 2 a little bit more scrutiny here, okay? So the way we're going to do that is we'll take limits of the derivative as we go to 3 pi over 2 from the left. So as we kind of approach 270 degrees, as we approach 270 degrees from the left, we're going to see what's happening to the tangent line. And we kind of know what's going to happen, don't we? I mean, after all, the graph looks like this. And it kind of goes, right? It does something like this. We kind of know what happens as we kind of approach an angle over here, like the tangent lines are going like this, and it looks like the tangent lines are going to get more and more vertical as we approach 3 pi over 2 from the left. You see what I'm saying here? So we're going to look at what the slope of the tangent line as we approach 270 degrees from the left. Okay, there that thing is in its factored form. Okay. I'm going to kind of split this thing apart in a convenient way Does that make sense? I just put the 1 plus 2 sine theta and the 1 minus 2 sine theta together. But hey, what happens when I plug in 3 pi over 2 into the sine function? What's sine of 3 pi over 2? What's the sine of 3 pi over 2? Yeah, -1. So can I just straight up plug 3 pi over 2 into that first fraction? Yes? What am I going to get in the numerator if I plug in 3 pi over 2? In the numerator of that first fraction, what would I get if I plugged in 3 pi over 2? 1 minus 2 is -1. What about on the bottom? 1 minus 2 times -1 is 1 plus 2, which is 3. So what is the limit of that first fraction? -1/3. Yeah? What about the second fraction? Well, the second fraction is a little bit annoying because what does cosine go to? What's the cosine function go to? The cosine function goes to 0, okay? But it goes to 0 how? What is this thing, right? So this guy right here, as this thing goes to 0, how? Through negative numbers or positive numbers? Negative numbers, okay? And what about this guy down here? As theta goes to 3 pi over 2, as theta goes to 3 pi over 2 from the left, what's going on? What's that? Yeah, what's the denominator going to go to? Oops, sorry, guys. There's a typo right here. What should not be in this thing? There shouldn't be a 2 right here. Yeah, that is a critical typo. Right, okay. So what does the bottom go to as theta goes to 3 pi over 2? It goes to 0 how? Yeah, it goes to 0 through, but the whole thing is this thing goes to, it's of the form 0 over 0. Do you see what I'm saying? So what can I actually apply to this thing? L'Hopital, yes? Okay, so the first thing goes to -1/3. The second thing is of the form 0 over 0, and as such, I can apply L'Hopital's rule. Okay, there was no 2 here. Oops, that should not be there. Yes, I'm sitting there staring at that going, uh-oh, what is going on here? That was not what I got when I was sitting in my office. But there was a typo there. There's not supposed to be a 2. Okay. All right. So look, this 2 is not here. Okay. So this thing should not be a positive 1/3. What should it be? Good grief. Come on, Hammett. Right? And what about the other things? That's -1/3. What about the other thing? What's the derivative of cosine? Negative sine. What's the derivative of 1 plus sine of theta? Cosine of theta. Okay? So it's going to be -1/3. Okay, now what happens? Well, sine of theta. Okay, so think about this. What's this going to go to? Sine of theta, that's going to -1, but the negative of that is going to where? That's going to 1. Does that make sense? Yeah? What about the cosine function? What is that doing as theta goes to as theta goes to 3 pi over 2 from the left? Cosine is going to 0 how? Through negative numbers. Yeah? So what's 1 over a tiny negative? What's 1 over a tiny negative? What's that going to go to? That's like going to be -infinity. Do you know what I'm saying? That's going to be like -infinity, but then if I multiply that by -1/3, what is it really going to on the whole? Positive infinity. Positive infinity, that's right. Okay, oh, look, I actually I'm fixing some stuff here now, yeah? So I actually fixed the 2 on this. I don't know why it's there and then not there. Do you see that? Look at that. Ridiculous. What is happening? Okay, I accidentally had some kind of typo. But the last thing here, this is absolutely correct. And you get positive infinity as the limit. But that's kind of what we expected, right? I mean, think about the slopes of these curves as we go to 3 pi over 2. Okay, the slopes of these tangent lines, it's getting closer and closer and closer to this vertical thing, yes? And therefore, the limit of the slopes is infinity for this thing, okay? So there is a vertical tangent, in fact, a cusp, okay? This is often referred to as a cusp at theta equal to 3 pi over 2. Okay? So we have a vertical tangent there. So once again, we have horizontal tangents at pi over 2, at 7 pi over 6, and at 11 pi over 6, yes? And we have vertical tangents where? At pi over 6, at 5 pi over 6, and at 3 pi over 2. That's where we have some vertical tangent lines going on. Okay? So here's a little picture of the whole thing here. See that? So there are the horizontal tangents, and there are the vertical tangents there. Yeah? I think that's pretty interesting stuff for sure. Any questions on that? Questions? Yeah.
So with this shape, how does that, so there's like a point 0, 0, how does that play into like the differentiability? Because like in the x, y coordinate plane, if you at a point, you can differentiate the slope at that point, right?
Yes. So what's your question again?
So like how does that play into, like is that the same for this point in the polar coordinate system?
Well, but what does this correspond to, Daniel? That point right there corresponds to which angle? Theta equal to what? That point is xy equal to 0, 0. But that happens when theta is 3 pi over 2. So like, depending on what angle you're at, you're going to be at different points on this curve. Yes? Okay? And eventually you're at this point. You're not at that point when theta is 0. When theta is 0, you're like right here. Does that make sense? That's where you are when theta is equal to 0. But you're at this point when theta is equal to 3 pi over 2. Yeah, and so what this is saying is at the point in time when the parameter is 3 pi over 2, you have a vertical tangent line. What is the xy coordinate of that point? 0, 0, yes? It's like x comma y is equal to r cosine of theta, r sine of theta, right? But what is that equal to? What is that equal to, Daniel, when theta is equal to 3 pi over 2? Because if you plug in 3 pi over 2, the sine function is -1, correct? So r is 0 at that point. So you would end up getting 0 for that. And on the other hand, the radius is 0 in both coordinates. So I happen to be at the origin when that happens. Does that make sense? And this formula that I came up with for the derivative tells me what the slope of the tangent line is, given a value of the parameter we're at. If I were to plug in theta equal to 0, I would probably get I would get some kind of positive slope. Does that make sense? Okay. And which way are we moving around this curve, just to make sure we're on the same page? Sort of start right here, and I go like this direction around the curve. Does that make sense? I'm going like this, okay? And then I'm back to the beginning once I get to 2 pi, okay? It's interesting stuff. Okay, other questions? Okay, so that thing, what's this angle? What did we say that angle was? Where that happens? Pi over 6. Of course, this guy, right? This guy is just pi over 2. No one's fretting about that, yes? Now what about this guy right here? What is that? 5 pi over 6. Okay, what about this guy right here? Yeah, that's 7. Oh man, this is getting complicated, right? 7 pi over 6. And then of course this guy over here. What's that? That's 11 pi over 6. Yeah? 11 pi over 6. And of course, 3 pi over 2, which is straight up and down, is where the tangent line goes vertical again. Yeah? Is that making sense? Hopefully? Hopefully this kind of polar stuff is, we're getting used to thinking in this way. Okay? I wanted to say a couple more things, and then we'll be done. Suppose that f of some angle is 0 for some specific angle. We'll call that specific angle alpha. Okay? So I don't know, alpha could be pi over 4, could be something, right? But the derivative, f prime of alpha, is not 0. Now remember, r is equal to f of theta. Does that make sense? So what I'm saying is the radius itself is 0, but the derivative of that radius formula with respect to theta is not 0. Then this was the formula we came up with for dy dx. What that would mean is if I plugged in alpha, then these two things would drop out. Okay? And I would be left with just this. I would be, right, these guys would be gone and I would be left with just this. Do you see that? Okay? And what cancels? What would cancel? Well, f prime of alpha would cancel, and I would just be left with sine of alpha over cosine of alpha. Do you see that? But that's just tangent of alpha, yeah? So where are we? Think about it. If f of alpha is equal to 0, that means the radius is 0, which means where are we sitting? Where are we sitting at? If f of alpha is 0, where are we sitting? The origin. We're at the pole. Does that make sense? If the radius is 0, we're at the origin. Yeah? So specifically what we're talking about here is what happens when to tangents at the pole. We just saw one. We saw one place where that happened at 3 pi over 2 just now. Yes? Back in the last example, 3 pi over 2 was a place where that happened. Since alpha is just a constant, that slope is constant. It's not changing. Okay? That means that the line y equal to tangent of alpha x is the tangent line. Okay? And it goes through the origin because we're at the pole. In polar coordinates, that's just the line theta equal to alpha. Remember last time we talked about that? Like tangent of theta is equal to y over x. Yes? And we can kind of solve for that y in terms of x. We end up getting this formula right here. This would be the formula for our tangent line. There. That's the same thing as the line theta equal to alpha, though. Okay. So I just want to at least mention this and write it down in a little theorem. This is in the book. It says if f of alpha is 0, and again remember r is f of theta. That means we are at the origin. Don't forget about that. And f prime of alpha is not 0, then the line theta equal to alpha is tangent at the pole to the graph of r equal to f of theta. Okay? So theta equal to alpha is tangent at that pole. Okay? So here's an example. Suppose that f of alpha is equal to 3 sine 5 of theta. Find the tangent lines at the pole. Well, let's do it. Okay, so first of all, we need to take the derivative. How do we take the derivative of this thing? What would we have to use? First of all, the derivative of sine is just cosine, but then we would also have to apply the what? If I'm taking the derivative of this, I would also have to apply the chain rule, yes? So I'd have to multiply by 5. So it'd be 15, or 3 times 5 is 15 cosine of 5 theta. And when is that 0? Well, that's equal to 0 when 5 theta is equal to 90 degrees plus any integer multiple of pi. I can just move by 180 degrees in any direction. So if you divide through by 5, then you're going to get pi over 10 plus any integer multiple of pi over 5. Okay, so that's when the derivative is 0. Okay. Wait, hang on a second. Something's not right with this. What should I have been looking for? Not places where that happened. Sorry, let me back up here. Where should I, okay, I want places where what is 0, not the derivative, but what? Just the sine function. Okay, so what you would do is you would take this guy, so you would say f of theta needs to be 0. So that means I would set what equal to 0? Sine of what? Sine of 5 theta would need to be 0. Where is the sine function equal to 0? Yeah, so that would mean that 5 theta would have to be equal to any integer multiple of pi. Yeah? Any integer multiple of pi would do the job. So that means that theta would have to be equal to what? Yeah, any integer multiple of pi over 5. Does that make sense? So where does that happen? You could take n equal to 0. So like theta could be, like if n is 0, you would get 0. Where else? I could take n equal to 1, yes. And so that would give me what? Pi over 5, yeah. Where else? 2 pi over 5, okay. Okay, 3 pi over 5, etc. Okay, I just wanted to kind of point this out. But of course, I would need to make sure that the derivative was not 0 at the same time. Does that make sense? But those would be the tangent lines at the poles here. Okay, so you have like, you have this guy, theta equal to 0 is this, theta equal to pi over 5, I'm assuming is basically this. Theta equal to 2 pi over 5, I think probably is basically this, okay, or something. Okay, and so you could kind of go around and see all of these different tangent lines at the origin. Does that make sense? I at least kind of wanted to point that out just so that you're aware of that. I'm not expecting you to like memorize these things, but I want you to be able to work through them, okay? Any questions on that? Questions? Okay, so let's go ahead and leave it at that.